In this video lesson, we are going to learn how to find a spanning set for a given vector space whose size is just enough. A spanning set that doesn't have a redundant vector, or in other words, a linearly independent one, is what we call as a basis for a given vector space. To recall some ideas from the previous lesson, let us recall that a spanning set for a given vector space is a set of vectors. Normally, this one is small, relatively smaller than the entire space, so that every vector from the given space is a linear combination of the vectors from the spanning set. Now, some spanning sets may contain redundant vectors. For example, if S is a spanning set for a given vector space B, in other words, the span of S is all of V, there may be some vector V in S, so that the span of S is equal to the span of S even without V is absent from S. In this case, we say that V is redundant in S. In other words, you don't actually need V to span the same set. It turned out that a linearly independent set of vectors does not have redundant vectors. Moreover, whenever your set is linearly dependent, the opposite of being independent, a redundant vector is present in the set. In linear algebra, we want to have a spanning set of vectors for a given space that doesn't contain a redundant vector, because we don't want redundancy in mathematics. Therefore, we actually want to have a linearly independent spanning set of vectors for a given space. If a given set of vectors is both linearly independent and spanning for the given space, we call it a basis for the vector space. As a quick example, we can consider the set E consisting of the vectors 1, 0, 0, 0, 1, 0, 0, 0, 1 from the vector space F3, where F is any field of scalars. This set actually forms a basis because every vector from F3 may be written as a linear combination of these three vectors. For example, if you get a vector xyz from F3, we may write xyz now as x times 1, 0, 0 plus y times 0, 1, 0 plus z times 0, 0, 1. Therefore, every vector from F3 is a linear combination of these two, so the span of E is the entire F3. Also, you can notice that this set is also linearly independent. It is because this vector, the second one, cannot be found in the span of the first vector, meaning to say this doesn't lie in the span of this vector, because this vector has a span consisting of vectors with 0, y, and z coordinates, whereas this vector has an element 1 in the y coordinate. Therefore, this cannot be found in the span of this vector. Also, the third vector cannot be found in the span of the first and the second vector, as the span of the first and the second vectors will contain vectors with 0 coordinate in the z place. Therefore, this vector cannot be found in the span of these two vectors. Hence, this set E does not have a redundant vector. That's a quick way to check if E is linearly independent. Therefore, E is a basis for F3. More generally, if you let n be any positive integer, and you let E sub I to denote the n vector with all zeros as coordinates except for a 1 on the I coordinate. The collection of vectors E1, E2, E3, and so on up to En forms a basis for Fn. This basis for Fn is sometimes what we call as the standard basis for Fn. You will see this later. In pictures, the picture shows us the geometric representation of the space R3. The vectors E1, E2, and E3 form a basis for R3. Here, E1 is the vector 1, 0, 0. E2 is the vector 0, 1, 0, while E3 is the vector 0, 0, 1. In physics, take note that these vectors are denoted by I, J, and K instead. This is why every vector in physics in a three-dimensional space may be written in the form xi hat plus yj hat plus zk hat. Next, let's consider the set of monomials consisting of 1 and the positive powers of x squared, x cubed, and so on. Take note that this forms a basis for the space R square bracket x consisting of all polynomials in x. It is because every vector, every polynomial in this space may be written as simply as linear combinations of this set. Furthermore, this set is known to be linearly independent because none of these vectors is redundant. In particular, if we consider the subset B sub n consisting of the polynomials or the monomials 1, x squared up to x to the nth power, this set only forms a basis for the space Rn square bracket x. Take note again, Rn square bracket x contains all polynomials of degree at most n. These vectors or these polynomials can only generate polynomials up to degree at most n. If we now consider the space Rn, where n is the set of natural numbers, this space consists of all functions f whose domain is n and whose range falls to be a subset of R. Note that each element of this space, because it is a function from n to R, it may be described by simply specifying the values or the real values assigned for f of n for each natural number n. Hence, f may be identified as an infinite sequence of real numbers. The first term being the value of f assigned at 1, the second term being the value of f assigned at 2, and so on. So every element of this space is a sequence of an infinite sequence of real numbers. For example, for each I in n, let us define the function epsilon sub I to be the one so that it assigns a value 1 to n if n is equal to I. Otherwise, it will just assign a value of 0. So for example, when we talk about epsilon sub 1, we mean the infinite sequence with zeros as all the terms except for a 1 on the first coordinate. Like so. When we say epsilon sub 2, we mean the one whose second term is 1, all the terms are just zeros. Epsilon sub 3 is the one with zeros as all the terms except for a 1 on the third term, and so on. In this case, the collection of B consisting of the epsilon sub I forms a basis for Rn, because every function, for example, if we have the infinite sequence f, for example, the infinite sequence is the sequence 1, 2, 3, 4, 5, and so on, all right, then notice that we can just write f as a sum or as a linear combination of the epsilon sub I. Here the coefficient is I from 1 to infinity, right? Okay, so you may verify this equality that it holds. Furthermore, this set of functions is linearly independent. For example, you may be asked to find a basis for a given subspace of a particular vector space. Here, the vector space that we're talking about is the subspace of the space of all 3×3 real matrix consisting of all 3×3 real skew-symmetric matrix. So, if W contains all the 3×3 skew-symmetric matrices, then if you get an element from W, we know how W will look like. A typical element of A, because A is real skew-symmetric, all the diagonal entries are zeros, remember? And if an element A is placed in the 1, 2 position, then it must follow that the element 2, 1 must be minus A. If we place an element B on the 1, 3 position, then a minus B is required on the 3, 1 position. Also, if we put an element C on the 2, 3 position, because A is skew-symmetric, there must be a minus C in the 3, 2 position. So, if A is 3×3 real skew-symmetric, we may write A as shown for some A, B, and C. Take note that we may express this as A times 0, 1, minus 1, and then all zeros, plus B times 0, 0, 1, 0, 0, 0, 1, 0, 0, minus 1, 0, 0, plus C times 0, 0, 0, 0, 0, 1, 0, minus 1, 0. Therefore, we were able to express A as a linear combination of these three matrices. Therefore, the span of these three matrices, so if we will call this as the matrix, let's say A1, this is the matrix A2, and this is the matrix A3, then we can say that the span of A1, A2, and A3 is the space W. Furthermore, we can check that the set consisting of these matrices A1, A2, and A3 is linearly independent. Therefore, the set A1, A2, A3 forms a basis for W. Okay, I hope that you get the idea of this example. Before I continue, may I remind you that you could always pause and rewind if you find the discussion fast. Also, please don't forget to list down some questions that may be raised while watching this video. We will answer all of them in our synchronous session. Let us now have the following exercise. So here I get a space W or a subspace W of R3 spanned by the vectors W1, W2, and W3. So here, V1 pala, I'm sorry, V2 and V3. So W here is spanned by V1, V2, and V3. So here you are asked to find a basis for W. Now take note that the vectors v1, v2, and v3 already form a set of spanning vectors for the space W. So if these vectors form a linearly independent set, then this set of vectors already form a basis. If not, one of the vectors here may be redundant, one or more. So we would like to remove the redundant vectors if there is any. So to know whether there is a redundant vector, we check for linear dependence. So this is the next step. And how do we check for dependence? To check for dependence, we would like to set up this interesting equation, right? If we can find values for AIs which are not all 0, therefore the set v1, v2, v3 are linearly dependent, and therefore one of these vectors has to be redundant. So here we try to solve for the possible values of a1, a2, and a3. If the only solutions are zeros for each of the AIs, then the set is linearly independent, and then therefore the set consisting of the VIs already forms a basis for W. If not, you have to identify redundant vectors. Alright, so we proceed by writing the equation this way, okay, and then simplifying. We get the following vector equation. Equating corresponding coordinates, we get the following linear system. Take note that the resulting linear system is a homogeneous linear system. So there are only two cases. Either you only get a trivial solution, in that case that means or that translates to linear independence, or you get a non-trivial solution, in that case that's linear dependence. So to know whether there is a non-trivial solution or not, we proceed by applying or performing the Gauss-Jordan algorithm. So we set up the augmented matrix for this linear system. That is the augmented matrix. Now we simply run a Gauss-Jordan algorithm and reduce it to a matrix in reduced row echelon form. So for this, I'm going to use GeoGebra to calculate the RREF of this matrix. So let me switch to the GeoGebra screen. So I hope that you can still hear me. So here I'm going to type in some data. Okay, so I'm going to call it a matrix A for the meantime. For the first row, we have 1, 0, 1, 0. For the second row, we have 1, 1, 2, 0. For the third row, we get 0, 1, 1, 0. And when you press enter, you get the following matrix A. Now, we just type in reduced row echelon form, so there. So you just replace that by A, press enter. So that is the reduced row echelon form. So I'm going to copy the reduced row echelon form over here. 1, 0, 1, 0, 0, 1, 1, 0, 0, 0, 0, 0. Alright. So let me go back to the original screen without GeoGebra. Alright. Remember, when solving for a linear system, after reducing the augmented matrix into RREF, we have to look at the pivots that we have obtained. In this case, we only get 2 pivots corresponding to the unknowns A1 and A2. And therefore, this indicates that the variable A3 is free. Because there are free variables in this case, the field of scalars is R, therefore there are infinitely many solutions. So aside from the trivial solution, we get a lot of non-trivial solutions. Therefore, as a conclusion, this set of vectors is linearly dependent. This is the conclusion. So therefore, there must be some vectors here which simply falls in the span of the others. But how would you know which one is redundant? Now, what you do is you try to solve for particular solution that is a non-trivial one. So for example, here we may write the general solution for A1, A2, and A3 as follows. Because A3 is free, we can set a value for R for it. Using the second equation, you get A2 plus A3 equals 0. Therefore, A2 is minus A3. This is minus R. And using the first equation, A1 plus A3 equals 0. Therefore, A1 is minus A3. So this is also minus R, where R is a real number. So simply choose or select any value of R different from 0. So take R to be 1. So here you get values A1, A2, A3 be what? Minus 1, minus 1, 1. Therefore, this says that minus 1 times V1 plus minus 1 times V2 plus 1 times V3 gives us the 0 vector. This is why the collection V1, V2, V3 forms a linearly dependent set. Now, do you remember the previous lecture? To determine which vector is linearly independent, we select the last coefficient that is non-zero. So here, the last coefficient that is not 0 is this one. What we do is we try to solve the vector, or we try to express this vector in terms of the other. So in this case, V3 is V1 plus V2. In other words, V3 simply lies in what? The span of V1 and V2. Therefore, V3 is redundant. Okay? V3 is redundant. So you can remove it from the set. Because it is redundant, still you're not changing the span. So as a conclusion, W is also the span of V1 and V2. In other words, you don't need V3 there to span the same space, W. Now to check whether the set consisting of V1 and V2 already forms a basis, we again check for independence or linear dependence. So you basically now are setting up this equation once again. So without this, so you only get two equations in the homogeneous linear system. But as you will see, what will happen is that after performing this, you only get to have the following as the RREF. This will be erased, and therefore in this case, what is the conclusion? A1 and A2 will be forced to become 0. And therefore, V1 and V2 form a linearly independent set. So the strategy is the following. So if you check for the dependence of the original set, you will be ending up solving a homogeneous linear system. Then you're performing an RREF, no? So the columns that does not contain a pivot correspond to vectors which are redundant. So if there are more than one column with no or without pivot, these columns that correspond to columns without a pivot corresponds to redundant vectors. So in this case, only one column doesn't have a pivot, therefore only the third vector is redundant. So in this case, we can say that the set V1, V2 is a basis for W. So the trick is you just look for columns that doesn't have a pivot. They correspond to redundant vectors. Okay? Now this next result generalizes the previous exercise, that if you have a finite set of spanning, if you have a finite set S of vectors that spans a given space or subspace of a given vector space, then this set S actually contains a basis. The idea is that if S is a spanning set, then if it is already linearly independent, then it's already a basis for W. But if not, according to the previous theorem, one of the vectors must be redundant. Alright, so you remove it from the set and then check for dependence once again. If the resulting set of vectors is linearly independent, then that is already a basis. But if not, then again, one of the vectors must be redundant. You remove it again from the set until you continue to repeat the process until you obtain a linearly independent subset of S. In that case, that is already a basis because you do not really change the span by deleting redundant vectors. So I don't think I need to prove this theorem anymore. And therefore, as a consequence, a finite spanning set of vectors for a vector space V must contain a basis for V in particular. So in other words, to get a basis from a spanning set, you may eliminate the redundant vectors. Okay? So in other words, a spanning set may be too many to span the set because of redundant vectors. If you were able to eliminate these redundant vectors, what results is a linearly independent spanning set, and therefore a basis for V. The next thing that we're going to do is we're trying to prove that if you have two or more, now it is possible for a vector space to have two or more bases, plural for the word basis. We will show that for a given vector space, if you have two bases, then these bases must have the same number of elements. But in order for us to prove that, we need the following result, which is sometimes called in linear algebra as the Steinitz replacement theorem. You will see the name, why the name of the theorem uses the word replacement in the proof. Okay, so I want you to watch carefully and take note of the proof, because the proof is really important here. So here you get a vector space V that is spanned by a finite set S, V1 up to Vn. If so basically S is a spanning set for V. Now if you have another set I with M elements this time, W1 up to Wm, and you found that that I is linearly independent in V, no? Then what is the conclusion? M must be less than or equal to N. In other words, let's say you have a vector space and you find a set of 7 vectors that spans the given space. So what is the conclusion? As a conclusion, you will never be able to find an independent set that has more than 7 elements. In fact, any linearly independent subset of V must have M elements where M is less than or equal to N. So in other words, the number of elements in an independent set cannot exceed the number of elements in a spanning set. It's always the case that spanning are more than the independent. So it's like that. So how do we show this? So for the proof, we use indirect proof. So we suppose that M is actually greater than M. What will happen? So here we are expecting a contradiction to happen because we suppose that m is greater than n. So first, let us consider the element W1. W1 comes from I. Since the span of S is V, and of course W1 is just an element of I, which is a subset of V, then W1 itself is in V. So therefore, W1 is in the span of S, so by definition, W1 may be written as a linear combination of V1 up to Vn, meaning to say, there are scalars AI, so that W1 may be written in this form. And take note that at least one of the AI must not be 0. Why? Because if all of the AIs are 0, what will happen is that W1 will become 0. Remember that whenever a set of vectors contains the 0 vectors, it cannot be linearly independent. Automatically, it will be linearly dependent. Do you remember that as a fact from a previous lesson? So therefore, these AIs cannot all be 0. Otherwise, W1 will be 0, and that will be an element of an independent set. That is not possible. So at least one of these AIs must not be 0. Okay? So without loss of generality, if one of these is not 0, let's just say that A1 is the one that is not 0. Okay? So if A1 is not 0, we can isolate this term, put all these things here on the left, and then because A1 is not 0, we can multiply its multiplicative inverse on the left, okay, to be able to isolate the vector V1. So I did that here as a I did the computation in the backstage, and I was able to isolate V1 as such. This expression is possible because A1 is not a non-zero scalar. Alright? So that's it. So as you can see, I was able to express V1 simply as a linear combination of W1, V2, and up to Vn. Hence, if V is the span of V1 up to Vn, and V1 is just in the span of W1, V2 up to Vn, then basically you can replace V1 by W1 in the set and get the same span. Because whatever V1 can do, W1 can also act in behalf of V1. Do you understand that? Okay? Because V1 is just, again, because V1 is just in the span of W1, V2 up to Vn, then you can replace V1 here by W1. That's why the theorem is named Steinitz replacement theorem. So W1 replaced V1, okay, in its place as a spanning set of vectors for V. Okay, so now we have found out that if we replace V1 by W1, the resulting set is still a spanning set for V. So here now, we next consider W2, the second vector in the set. Okay? And W2 is, of course, a linear combination of W1, V2, V3 up to Vn, in which at least one of the coefficients. Now, by the way, because W2 is in the span of this, W2 is a linear combination of this. Now, in which at least one of the coefficients of the VJs, when one tries, let's say you were able to write W2 as, let's say, A1 W1, A2 V2, A3 V3, okay, A and Vn. If you were able to write W2 as such, notice that the AIs starting from A2 up to AN cannot all be 0. Because if all of these underlined scalars are 0, so this will be 0, if all of those are 0, W2 will just be a multiple of W1, therefore W2 is in the span of W1. that will mean that W2 is just dependent on W1. So this set will be linearly dependent. Of course, that is not the case because I is assumed to be linearly independent. So therefore, one of these scalars, A2, A3, An, must be non-zero. Okay? So, without loss of generality once again, let's just say that A2 is the one that is not zero. Otherwise, you can just interchange with some other, interchange indices with some other terms. So let's just say that the coefficient of V sub 2 is non-zero. Then, once again, from the last equation, you can, because this is not zero, you can actually solve for V sub 2. And you will see that if you try to solve for V sub 2, you put everything on the left, this also. You will be able to write the V sub 2 as a combination or as a linear combination of W1, W2, V3 up to Vn. Okay? Hence, a while ago, V is the span of V1, W1, V2, V3 up to Vn. Because V2 can be expressed as a linear combination of W1, W2, V3 up to Vn, then you can replace the V2 by W2. In other words, the job of V2 can be performed by W2. So, here we just continue repeating the process. Now here we are under the assumption that M is greater than N, meaning to say there are more W's than V's. In the end, what will happen is that everything in S will be or gets replaced by a W because there are more W's than V's in our assumption. There. So we next consider W3, and once again we repeat the argument above until we get V as a span of W1 up to Wn. Anong nangyari? Each one of these now was replaced by W. Now take note that M here is different from N. M is actually greater than N. So aside from W1 up to Wn, there are more W's available. So in other words, there is still Wn plus 1. This will happen because, again, just like what I've said, M is greater than N. And because M is greater than N, W sub N plus 1 still exists. And because this is just a vector from V, W N sub N plus 1 will be in the span of W1 up to Wn. And that will mean that this set, it will be linearly dependent. Of course, that is the needed contradiction. Okay? Therefore, M must be less than or equal to N. Alright, so remember, if you have a spanning set with N elements, then any independent set must have at most N number of elements. It follows as a consequence that if you have a finite basis B, then every basis of V is finite and has the same number of elements as V. Why is that the case? Because if you have a finite basis B, let's say B has N elements, then of course B is a spanning set. Every basis for V must have a finite number of elements as well because a basis is independent. According to the theorem, if you have a spanning set with N elements from the set, then any independent set will have at most N elements. Therefore, any basis will have at most N elements, therefore finite. In fact, if you have two bases for a given vector space, they must have the same number of elements because if, let's say, you have two bases, B1 and B2. So you can think of them as two different bases, right? Now, a basis is linearly independent and spanning at the same time. So if you think of B2 as spanning and B1 as independent, then by the theorem, we can say that the number of elements in B1 is less than or equal to the number of elements in B2. Also, we can think of it the other way. You can think of B1 as spanning, B2 as independent, and in that case, B2 will have the number of elements less than or equal to the number of elements of B1. And when these inequalities hold, that will imply that the number of elements in B1 equals the number of elements in B2. Okay? With this, we can now have the following definition. If a vector space over F has a finite basis, of course, every basis will have the same number of elements. The number of elements in that basis is what we call as the dimension of V. By the way, if V has a finite basis, we say that V is finite dimensional. The dimension of V over F is denoted by this symbol. If V has no finite basis, we say that V is infinite dimensional. Or if we cannot find a finite spanning set for V, for example, we can say that V is infinite dimensional. For example, the space Fn, or if F is R, this is the space Rn. This is n-dimensional because a basis for Fn is the standard basis E1 to En. Do you remember this? Any basis for Fn will have n elements exactly, according to the previous theorem. The space of m by n matrices, has dimension. What's the dimension? For example, if you're looking at M23, a matrix in M23 looks like this. How many matrices do you need to specify a matrix in M23? So, well, hindi ba? You can write this as 1, 0, 0, 0, 0, 0 plus B times 1 here, then all zeros, plus C times a 1 over here, plus D times a 1 over here, plus E times a 1 over here, plus F times a 1 over here. So as you can observe, as you may want to observe, this forms a basis for the space M23. The space of 2 by 3 matrices over F. So in this example, there are 6 elements in a basis. Because we were able to find a basis consisting of these matrices that is for the space M23. In general, what is the number of elements in a basis for M, the space of M by N matrices over F? Take note that since there are M rows and N columns in an M by N matrix, then all in all there are M times N entries. And each of this entry needs to be specified by an element from F in order for us to have an M by N matrix. Therefore, in general, Mn, there are Mn matrices in a basis for the space M and N all over F. Next, consider the space R square bracket X of all polynomials. Okay? In a previous example, we have shown that the space R square bracket X of polynomials over R cannot be spanned by a finite number set of vectors. Therefore, this set cannot have a finite basis, so the space is infinite dimensional over R. However, the space Rn square bracket X consisting of polynomials of degree at most n may be specified or is the span of the monomials 1x x squared up to xn. In fact, this is a basis for the space Rn square bracket x, and therefore the space Rn square bracket x is finite dimensional, and the dimension over R of Rn square bracket x has to be n plus 1, because there are n plus 1 elements in this collection. Also, the space C of complex numbers over R is of dimension 2. Okay? Why? Because we need two real numbers, minimum, to specify a complex number. Remember that every complex number may be written in the form a plus bi, where a and b are real numbers. Actually, whenever we say this, a plus bi is actually of the form a times 1 plus b times I. Therefore, C is spanned by the complex numbers 1 and I. You can check that 1 and I are linearly independent. However, in the case when the field of scalars is C, if we allow the scalars to be complex numbers, the dimension of C over itself has to be 1. I want you to think about this one. So let us determine the dimension of the space of 3 by 3 real symmetric matrices. Now take note that a 3 by 3 real symmetric matrix is of this form. In other words, if one has specified B on the 1, 2 position, then automatically B must be there on the 2, 1 position because the matrix is symmetric. If you're forming a symmetric matrix and you put a C on the 1, 3 position because the matrix is symmetric, on the 3, 1 position there has to be a C as well, and so on. So here, take note how many letters did we need minimum to specify or to describe a 3 by 3 real symmetric matrix. Here, as you can take note, we only needed 6, A, B, C, D, E, and F. Actually, what that actually means is that we can write this as a combination of these matrices. C times 1, 1 plus D times 1 plus E times 1, 1 over here, and then F over here. So take note that the blanks here actually mean 0. So we need 6 matrices to specify every 3 by 3 real symmetric matrices. Therefore, and in fact, these 6 matrices form a linearly independent set. You can check that because this cannot be found in the span of this. This cannot be written as a combination of those. This cannot be written as a combination of the previous 3, and so on. So the answer to this question is 6. Okay? Alright, so this is another exercise. So here I have two subspaces of R4. W1 is the set of vectors x, y, z, w, satisfying the equation x plus y minus 2z plus 3w equals 0. The second subspace is W2, consisting of the vectors x, y, z, w, where z is equal to w. So remember that if you have two subspaces, we can take their intersection, and the intersection is another subspace. So here, the exercise wants you to find a basis for the intersection of W1 and W2. And you may find this exercise in, a a lot of lessons in linear algebra. Find a basis for this, find a basis for that. Because remember, a basis is what we need to be able to describe the entire space without specifying all the elements in the space. If you specify a basis, you know everything in that space. Okay? Take note also that once we have found a basis for the intersection, we can now determine the dimension. So, how do we find a basis for the intersection? So, what we wanted to do is we describe the elements in the intersection. So, take note that if x, y, z, w belongs to the intersection, what happens is that x, y, z, w must satisfy both of these conditions. No? So this means that x plus y minus 2z plus 3w equals 0. At the same time, z is equal to w. But the second equation translates to, or you can rewrite that to as z minus w equals 0. So what we have really is just a 2×4 homogeneous linear system to solve. So in order to describe the intersection, we have to solve this linear system. So we want to run a Gauss-Jordan algorithm to this matrix. So in this case, we don't really need GeoGebra because I think this will work. In just a few steps, we can try to transform this into RREF. For example, this is a pivot. Pivot in the first row is present. A pivot in the second row is already present, but this has to be eliminated. So we perform E1, 2, 2. So we get the following: 1, 1, 0. 3 plus negative 2 is 1, 0. There you have it. So this is already a matrix in RREF. These are the pivots. Okay? So therefore, x, y, z is in the intersection if and only if. How do we describe the points in the intersection? So here y and w are free. So we can write this as what? If y and w are free, I can write y as r, for example, and w as s. Okay? So if y is r, w is s, how do you solve for x sub 1? So you look for this equation. As you can see, x is minus y minus w. This is minus r minus s. And if you want to solve for z, you look at this equation. That's z minus w equals 0. Therefore, z is w. So z is s. And as you can see, this gives you the solution set for the linear system. But we wanted to describe this, or we wanted to find vectors that can span this intersection. So we would like to write this as follows. So you collect all those with r, this minus 1, 1, 0, 0, and those with s, this is minus 1, 0, 1, 1. So as you can see, every vector in the intersection is a linear combination of these two vectors. Therefore, is the span of minus 1, 1, 0, 0, comma, minus 1, 0, 1, 1. I think that's it, no? And do you think this set is linearly independent? Yes. How do you know? If there are only two vectors, you just need to verify that one is not a multiple of the other. Is this a multiple of that? Not really. So therefore, that forms a linearly independent set. Therefore, if you consider the set consisting of minus 1, 1, 0, 0 and minus 1, 0, 1, 1, this is already a basis for W1 intersection W2. There you have it. Okay. So here we get another theorem, but this time, last time, we obtained a basis from a spanning set, right? This time, we obtain a basis from an independent set. So we're going upwards. So V is a finite dimensional vector space. And then G is a finite spanning set for V. And that I is linearly independent subset of B that is found inside or as a subset of G. Remember that independent sets tend to be fewer than spanning sets. So in this case, in particular, I is actually a subset of G. Then according to the theorem, between I and G, there is a basis that falls between them. So you can think of independent sets as, well, a set with a few vectors. Sometimes it's so few that it cannot span the space. A spanning set may be too plenty to span the space, therefore, because there may be redundant vectors in it. So somewhere in the middle, there is a set that is just of the right size to span the space, and that is a basis. The proof is very simple. So if the independent set I already spans V, then just take B to be I. We're done. But if the span of I is not yet V, hence I is not G. Okay? So something from the spanning set that is not in I must be there. So let's call it G1. So that this G1 is not found in the span. So what we do is you just combine G1, right, to I, join G1 to I using union, and still this is linearly independent because G1 is not in the span of I. I mean, G1 is not redundant even if you put it to I. Again, if the span of this union is already V, we are done. You take this as your B. If not, we can repeat the above argument, so you can produce another G2. So you just put more vectors to I coming from G, but you have to be careful every time you put another vector to I, you have to make sure that what results is an independent set. You can continue this process until you get a basis for V. And this M will actually exist because G is a finite spanning set. Okay? I'm so sorry. As a consequence, every linearly independent subset I of a finite dimensional space V may be extended to form a basis. So if you get an independent subset of I, last time you get a spanning set, you can reduce it to a basis. This time, if you have an independent subset, it may not be a basis, but it can be extended to form a basis. So what you do is, if this is your independent set, so you look for a known basis. Normally, in the case of Rn, you just, what? You just use the standard basis because that's already a basis, right? You combine it with I, or you take the union of B with I. Of course, this time, if this has many vectors, obviously some of this will be redundant. Then use the previous theorem. Obviously, this is a spanning set. Then use the previous theorem from last time to guarantee that a basis B star can be found between I and G. So that's it. So let's exhibit this in an exercise. Okay? So here you get V1 and V2 as vectors from R4. So what we do is we show that I consisting of V1 and V2 are independent of one another, or they form a linearly independent set over R. This is quite easy, because every vector spanned by V1 is of the form AA0, right? Multiples of V1 can consist of AA00. But I don't think V2 is of this form, so V2 cannot be found in the span of V1. Sorry, V2 is not found in the span of V1, hence, if you combine V1 and V2 together, this is linearly independent. So that's it. So the real exercise here is to extend this to a basis for R4. Well, we know because R4 is 4-dimensional, these two vectors is not enough to become a basis for R4. We need two more elements. Now, what would be those two elements, or how do we extend this? From here, we will follow the theorem. We will obtain a well-known basis for R4. So a well-known basis for R4. Well-known basis. So I think let's write it this way. Here. I'm sorry. Let's write it here. So a well-known basis for R4 is typically the standard basis 1 0 0 0, 0 1 0 0, 0 0 1 0, and 0 0 0 1. Alright, so this is a standard basis for R4. So what we do is we take the union of I with E, just like before. So we're going to put here, so let me call this E1, E2, E3, E4. Okay, so I union E will be V1, V2, E1, E2, E3, and E4. So there are 6 vectors. Obviously, 2 of these must be redundant. So we have to expel 2 of these 4 to be to have a basis. So what we do is we check for dependence as always. So we set up the following equation: A1V1 plus A2V2 plus A3E1 plus A4E2 plus A5E3 plus A6E4 equals 0, 0, 0, 0. Okay, and then we look for non-trivial solutions for A1. You look for the what do you call this? You look for the redundant vectors. But I've already taught you how to find redundant vectors, right? Now this will give us a homogeneous linear system. Now you can check using your own computation that the homogeneous linear system will actually look like this. Okay, what do you notice? What is the shortcut? So this is going to be the homogeneous linear system in our case. What do you notice? As you can see, the first column is the first vector. The second column is the second vector. The third column is the third vector in the list. The fourth column is the fourth vector in the list. No? Fifth is this one. Sixth is this one. And then you just run the Gauss-Jordan algorithm. So let's switch back to GeoGebra. So here we will have to create another matrix. Let's say B. So the first row. So let's not put the last column anymore, because all of them are just zeros. I'm sorry. 1 1 1 0 0 0, comma 1 0 0 1 0 0, comma 0 0 0 0 1 0, comma 0 1 0 0 0 1. I think that's it. And then we will run the RREF B. So there is the RREF. So Upon reduction, or our EF, so we get the following. So I get here 1, 1, 1, 1, 0, negative 1. Then I get here a 1, 1, and negative 1. So all the rest are zeros. Yeah. So let me finish writing the matrix. Alright, so let me not forget the last column, which is 0. So let's switch back to the slide. Alright, so that's the RR, EF. Now, according to a previous example, so we look for the pivots. Pivot, pivot, pivot. And then you look for the columns that has a pivot. That doesn't have a pivot. So this doesn't have a pivot. That doesn't have a pivot as well. So there are two columns that doesn't have a pivot. Therefore, they are what? They are redundant. I mean, the vectors corresponding to these columns are redundant. So if this is the column corresponding to V1, V2, V3, E1, E2, E3, E4, so which ones are redundant? So E2 and E4 are redundant. Okay, so what happens is that what remains now, if we include E1 and E3 to I, you get a basis for R4 this time. That includes I. Okay, so that's it. That's how you extend a given set of vectors to form a basis. So in summary, so this is what we have learned. If you have a basis S, it is actually a maximal linear independent subset. When you say maximal linearly independent subset, mean to say anything more than that is no longer independent. Did you understand? And it is also a minimal spanning set in the sense that anything smaller than that cannot be a spanning set. Okay, so this statements explains those facts. In the case of an n-dimensional vector space, we can say that every set containing more than n elements must be linearly dependent, right? Because a basis with n elements has to be maximal linearly independent. So anything more than n should be dependent, and anything fewer than n cannot span V, right? And as a consequence as well, if you get a set of n vectors, once it is linearly independent, already it is a basis, right? Because basis is a maximal independent set. If your dimension is n, so a maximal number is n. So any linearly independent set with n vectors in it must be a basis. Or any spanning set with n vectors must be a basis. So in other words, if you are in R4, for example, that's a 4-dimensional space. If you were able to show that a set of 4 vectors is independent, already it's a basis. You don't need to show that it's spanning. Or if you were able to show that this set of 4 vectors is already spanning, you are in a 4-dimensional space, already that's a vector. Already that's a basis. So you only need to choose one because you already know the dimension of the given space. Bright idea. So the next aspect of a basis that we need to talk about is the basis as a geometric object. Actually, a basis, in other words, in layman's term, is just a set giving a coordinate system to a given vector space in some sense. Let me tell you about this property of a basis. Let's start with the following result. If you get a set B of vectors in the space V, and this set B is a basis for V, if and only if, so this is an if and only if statement, every element of V can be expressed uniquely as a linear combinations of the elements of B. In other words, there are unique scalars a1, a2 up to an, so that V is a1 v1 plus a2 v2 plus and so on and so forth. Okay? Take note again, when you try to expand this one, it means a1 v1, a2 v2 and so on, an vn. Now, of course, a basis is a spanning set. So when you have a given vector v in the space, it is always possible to write v as a combination of v1 up to vn. The thing here is because b is a basis, there is only one way to write v this way. No other set of scalars. There's only one set of scalars that exists that expresses v as a combination of the v sub j's. Did you understand the theorem? Kumbaga, being a spanning set allows us to write v as a combination this way. The independent part guarantees that such a set of scalars is unique. You will see that. For the proof, because this is an if and only if statement, so we prove two things. First, we suppose that B is a basis for V. We show that there are unique scalars a1, a2 up to an, so that this is true. First of all, since B is a spanning set for V, every element of V is a linear combination of the VKs. Talagang merong mga AKs. To prove the uniqueness, suppose that there are two different ways to write V as a combination of the VKs. For example, the one uses the coefficients AK, the other one uses the coefficients PKs, where these are scalars. Then, if I subtract these two, of course, they are both equal to V, that is 0. This is V, this is V, this is also V. So the difference is the 0 vector. But arranging the sum, that sum gives us the following sum. Okay? So this combination, so when you try to expand this one, it's like A1 minus B1 V1, A2 minus B2 V2, and so on, AN minus BN Vn equals 0. But since, look at this, these vectors v1, v2 up to vn is linearly independent. Whenever you have this equation, if the vectors vi's are independent by definition, the scalars must all be zeros. So each one of these must be zeros, and if each one of those are zeros, then AK must be equal to BK for all K. And that proves uniqueness. Why? Because if there are two ways, actually there isn't two ways. There aren't two ways, because AK in the end is just the same as BK. For the converse, suppose that every element of B may be expressed uniquely as a linear combination of the elements of V. Okay? Then already, by its statement, B spans V. So it remains to show that V is linearly independent to prove that B is a basis for V. How do we show that the VI's are independent? We again write down this equation. We suppose that A1 V1 plus A2 V2 plus and so on, AN Vn equals 0. We have to show that each one of the AKs are zeros. But how can we make that possible? Here, take note that the 0 vector is just 0 v1 plus 0 v2 plus 0 v3 and so on plus 0 vn. In other words, that is another way to write 0. This is one way to write 0. This is another way to write 0. From the uniqueness assumption, it must follow that this and this are equal. That AKs and the zeros are equal. In other words, that proves that AK must all be 0, and therefore B must be linearly independent. Okay? So what have we learned from here? So let's say you get a basis for V. This time, I'm going to call this an ordered basis. When I say ordered basis, this is not just a set. This time, we now consider this as a list. So you do not just interchange two elements. So the positions of these elements will be important. So V1 will remain the first position, V2 remains in the second position, and so on. Okay? So according to the previous theorem, there exist a unique scalars. There exist unique scalars, walang S. A1 up to AN, so that V is in this form. There is only one set of scalars that must satisfy this equation, according to the previous theorem, because this is a basis. These scalars now are what we call the coordinates of B relative to this basis. Let me explain that. Now, to put them in one coordinate, we use a column matrix. If we place all these scalars, these unique scalars, in columns, no, we call this the coordinate of V with respect to the ordered basis B. Of course, the constants that are found in this column matrix depends on your selection of basis. If one changes a basis for V, then you get another set of scalars for the vector V. To further explain this, let me show you this example. Consider the two bases, ordered bases for R2. The first one being the standard basis. The second one is B, consisting of 2, 0, and 1, 1. Now you can check that this is a basis because this is linearly independent and R2 is dimension 2. Take note that 1, 1 does not lie in the span of 2, 0. So when you look at them as vectors, the vector 2, 0, so this is the vector 2, 0. Sorry. And the vector 1, 1 is right here. This is the vector 1, 1. This is the vector 2, 0. One is not parallel to the other, or they don't fall in the same straight line, so they are independent. Okay? So let's consider the vector 7, 3. Take note that 7, 3, relative to the standard basis, it's of the form 7, 1, 0 plus 3 times 0, 1. Ito yung sa physics nyo, 7i hat, 3j hat. Therefore, the 7 and the 3's are the coordinate of V relative to the standard basis. This is why this is called the standard basis. So whatever it's here, whatever numbers are here, those are the coordinates relative to the standard basis. But for the second one, no? How do you write 7, 3 as a linear combination of 2, 0 and 1, 1? So we seek for scalars B1, B2, right? But remember, this is the same as solving for this linear system. This is the test vector. These are the given vectors. No? We have to solve this linear system. And solving this linear system on your own, you can pause this video. You get the following. 2, 3. Okay? That's 2 times 2, 0 plus 3 times 1, 1. And you know that there is a unique solution. Okay? Hence, the coordinate of V relative to the basis B, to the new basis B, is 2, 3. You see that the coordinate changes when you change a given basis. So, what is happening geometrically is the following. So, here, I'm depicting the vector V, which has component 7, 3, I think. So, this is the vector 7, 3. So this is the standard basis. This is E1, this is E2. They give us this grid, no? The standard basis gives us this grid, no? This is the 1 unit in the x direction. This is 1 unit in the y direction. The coordinate 7, 3 tells us to move 7 times in the direction of E1 and 3 times in the direction of E2. That's what you mean by the coordinate 7, 3. Right? That's what you mean by that. 7 of E1 plus 3 of E2 gives us V. Sorry. So you get this parallelogram rule, no? Just like in physics. On the other hand, if you consider the vectors 2, 0, so this is the vector now 2, 0 and 1, 1. Now, relative to this basis, we get another coordinate system. And the coordinate system that I am talking about is this coordinate system. As you can see, if this is 2, 0, we actually need, for this example, we need 1, 2, 3. We need 3 times 2, 0, and we need what's this? No. We don't need 3 times 2, 0. We only need 2 times 2, 0, and we need 3 times 1, 1 to get a sum equal to V. In other words, this is 2, this is 3. This is why the coordinate of V relative to the basis B is 2, 3. You need 2 of this and 3 of those to get a sum equal to V. So in this new coordinate system, the coordinate of the same vector V now changes to 2, 3. So the next question is, let's say given the old coordinate system, is it possible to obtain the coordinates of the same vectors in a different basis or in a different coordinate system that will not require us to solve for the coefficients anymore? Is that possible? Well, we have to use the following idea. So let's say you have 2 ordered bases for V. Both of them have n elements, so V is n-dimensional in this case. So let's say A has V's, B has W's. Suppose that for J, starting from 1 to n, so what we do is what we wanted to find. So these are the old basis vectors. This is the, you can consider this as the old and these ones are the new, as the new. And what we want to do here is we want to write each one of these old, because we're transitioning from the old to the new. We want to write each one of these as a combination, as a linear combination of the new ones, because we're transforming coordinates from one to the other. So for, let's say, for V1, I was able to write V1 as a combination of, in fact, you will be able to write V1 as a combination of this. So you collect all the scalars, you put them in column. Okay? For V2, you do that as well. So you write V2 as a combination of this. So you put them in column as well. Now, arrange the columns now in such a way that the first column, arrange these columns in a matrix in such a way that the first column is the coordinate of the first vector in the new basis with respect to the new basis. The coordinate of the second old vector with respect to the new basis be in the second column, and so on. The matrix that you will be getting is what we call as a transition matrix from A to B. And this matrix is what? It's written in the form T, and then you get A arrow B, but you see the arrow is in the reverse direction for some reason. I will explain this notation later, or the choice of this notation later. Okay? So to illustrate the definition, let me use this previous example. So you get 2 bases, E and B. E is the standard one, B is an invented basis for R2. So let's find the transition matrix from E to B. How do you do that? So in order to do that, you write each one from the old one, so there, as a linear combination of the what one? The new basis vector. So here we get, or we find A11, 20. Or should I use A? Let's use other letters. Let's say P11 plus P21. By the way, for you to be able to understand this choice of letters, so let me start with this. The transition matrix is a 2 by 2 matrix, right? Because there are 2 elements in each basis, so it will be a 2 by 2 matrix. So here, so you want to find this matrix such that, so let me write here. So let's find this such that the first column is the coordinate of the first vector in the old basis relative to the new basis. That means to say that if I write 1, 0 as a combination of the new vectors, new basis vectors, the first column will be the coordinates, meaning to say P11, 20 plus P21, 11. And then the second column should be the coordinate of the second vector. So P12, 20 plus P22, what? 20. I'm sorry, 11. But take note that each of this equation reduces to a linear system. So the first one reduces to the linear system 20, 11, 10. How did I know this? Here. Bale, this one should be the first column, this one should be the second column, and this one being the test vector should be in the last vector. And also this one reduces to the following 20, 11, 0, 1. Now here, take note that we are solving, although they seem to be of the same coefficient matrix here, they are solving for 2 different unknowns. Now the first one solves for P11, P21. The second one solves for P12, P22. Take note. But anyway, they have the same coefficient matrix, so why not solve them simultaneously? So we can solve them simultaneously as follows. So as you can see, these are the vectors from the new, and these are the vectors from the old basis. So we are solving this linear system, so you just run the RREF. So I think once again, let's use the GeoGebra. So don't worry, we are going to finish soon. So let's try to input another matrix, let's say C. Sorry. The first column should be 2, 1, 1, 0. The second row should be 0, 1, 0, 1. And then we're going to find the reduced row echelon form of the matrix C, which is as the following. The RREF gives us 1, 0, 0, 1. This gives us 0.5, 0, negative 0.5, 1. So that this means that this is precisely P11, this is precisely P21, this is precisely P12, and this is precisely P22. Alright? But as you can see, P's are as arranged, no? Seems to be this matrix. So the matrix that will appear here precisely is going to be the transition matrix. Okay? So the transition matrix that we actually need is the matrix 1/2. So let me change that to 1/2. Negative 1/2, 1. Now, what does that matrix mean? This means that the first column of this, no, if you're putting here 1/2, negative 1/2, you get this equation to be true. I'm sorry. No, that's not negative 1/2. 1/2, 0. And then this one is negative 1/2 is 1. So that will make the equations true. By the way, I forgot to switch. I'm sorry. Okay. I hope that you're still there. This lesson is quite long. You can pause and of course go back later. So this gives us the transition matrix. The question is, what is this transition matrix for? No? Now, do you remember whenever in the previous example we considered the vector 7, 3, the vector 7, 3, we found out that the coordinate of v relative to E is 7, 3, of course, while the coordinate of v relative to B is, I think, 2, 3. Is that 2, 3? Yeah. 2, 3. Yes, 2, 3. You can check, no? 2 times this plus 3 times that, you get 7, 3. Okay. 2, 3. Now, what we actually wanted to prove next is that what? The transition matrix helps us recover the new coordinate from the old one. As you can see, the old coordinate is 7, 3. Now, if you try to multiply, the transition matrix to 7, 3, this is the old one, the coordinate in E relative to E. You see that if you try to multiply this as matrices, you will get the new coordinate 2, 3. You can verify. Okay. You can verify that this is correct. In fact, that is our last theorem. The transition matrix allows us to transform the old coordinates to the new ones. Okay? Or connects the old coordinates to the new ones. So here is the theorem. So here A consists of V's, B consists of W's. These are ordered bases for a vector space V. Then, according to the theorem, for every V in the, I'm sorry, this is incorrect. This should be V. For every V in the vector space V, the coordinate of V relative to the basis B is equal to the product of the transition matrix from A to B times the coordinate of V relative to the basis A. In other words, transition matrix times old coordinate equals new coordinates. Okay, that's why maybe it's called the transition matrix. I will just outline the proof for you because this is kind of tedious, but this is the full proof, really. So let's say that the transition matrix has entries Pij. This is an n by n matrix, right? So this matrix being the transition matrix, from its definition, the jth column should be the coordinate of Vj. The jth column of the transition matrix is the coordinate of the jth V relative to the new basis. Remember that you are writing each one of the old basis vectors in terms of the new basis vectors. The coefficients, you collect them, you put them in columns. Okay? This means that Vj, now if you multiply this to W1, this to W2, this to Wn, you add them, you get V sub j. So this equation simply meant that. Let's write it in a more compact form. So let's now take an arbitrary v from v. Assume that the old coordinate of v, old because this uses the basis a, consists of a1, a2 up to an in columns. So this is what will happen. A's, the a1, a2 are the old coordinates of v, meant that if I can write v as a1, v1, these are the old basis vectors, a2, v2, an, vn. Now, according to the previous theorem, previous equation, if you use this is true for j from j equals 1 to n. So whenever you see v1, you replace the j by 1. If you see v2, you replace the j by 2, and so on. So you get the following. The v1 gets replaced by this. So you see that the 1 is replaced there. The j is replaced there. Here, this is v2. Okay. J was replaced by 2. And this is vn. J was replaced by n. Now, using properties of summation, you can bring this in, then combine all the w1s in one sum, combine all the w. So, as you can see, if you expand all of this, this consists of sums of w1 up to wn. So, you collect all the terms with w1, you collect all the terms with w2, you collect all the terms with wn. So, you can compute that this will be the resulting form. Okay, I will not show you the messy computation, but it will eventually lead to this. So this time, as you can see, originally v was written as a combination of the vi's, but then I was also able to write this as a combination of the wi's. Hence, I know now the coordinate of v relative to the new basis w. And then the new basis consisting of the w, the b. So the first coordinate is this, the second coordinate is this, the third coordinate is this, so that's it. But if you try to expand this sum, you will notice that that is the same as multiplying this matrix in this column. So for example, if I multiply this with this, I get this, right? P11 A1, P12 A2, P1n AN. And that's the sum. And so on. If I do this, I get that. If I do this, I get that. But as you can remember, this is the transition matrix and this is the old coordinate. And therefore, we're done. So this is the equation that we wanted to prove in the end. So I want you to wait for the exercise sheets to practice solving problems in this topic. So I want you to wait for the next lesson and see you in our live session. Thank you for listening.